Part A. If it's midnight in Tokyo on Saturday, October 28th, 2006. What time is it in London? 4 in the afternoon, 8 hours behind. But just one day later, on October 29th, when it's midnight in Tokyo, it will be 3 p.m. in London. London is suddenly 9 hours behind. How is this possible? Well, here's the answer. For 5 months, from the last Sunday in October through to the last Sunday in March, Britain uses standard global time known as Greenwich Mean Time. But from late March to late October, its clocks are moved 1 hour forwards, and it uses British Summer Time. British Summer Time, or Daylight Saving Time as it's also known, was first proposed in 1907 by a Londoner called William Willett. He had noticed that in the summer the sun had already been shining for several hours in the morning by the time most people woke up, but in the evening it was already getting dark by the time they were on their way home. He therefore proposed advancing Britain's clocks in April, putting them forwards by 20 minutes on 4 Sundays in a row, and then at the end of the summer putting them back on 4 Sundays in September, again by 20 minutes on each occasion. That way, British people would get an extra 80 minutes of sunlight every day from the beginning of May to the end of August. This proposal wasn't accepted at the time, and it wasn't until the First World War that daylight saving time was introduced in Britain as part of the wartime effort to save energy. When it was introduced in 1916, though the system, like today's, was simpler than the one proposed by Mr. Willett, the clocks were advanced 1 hour in spring and returned to Greenwich Mean Time in autumn. Some form of daylight saving time has been in use in Britain ever since. There have been some variations in the system. However, during the Second World War, for example, the clocks in summer were 2 hours ahead of Greenwich Mean Time. Later, from 1968 to 1971, clocks ran 1 hour ahead through the whole year. The main reason for this particular version of daylight saving time was to put Britain in the same time zone as the rest of Europe. This worked well for businesses, but it was hard on school children who lived in the north of Britain, who in winter had to go to school in the morning in complete darkness. In 1972, Britain returned to the original system, using daylight saving time only in summer. However, safety experts argue that putting the clocks back at the end of October makes driving more dangerous throughout the winter. They estimate that about 450 deaths or serious injuries are caused every month in the winter by that hour of evening darkness. Children are particularly at risk. In the morning, they usually go directly to school, but in the evening, they tend to spend more time outside, either playing or on their way to the houses of friends. Despite this disadvantage, however, there are for the time being at least no plans to change the current system. Part B. Tony. Ladies and gentlemen, let me welcome you to New Fiber Industries. We've called today's press conference to announce our discovery of a revolutionary new material, which for the time being we are calling X15. We believe it has the potential to transform the way we live. In a moment, I'm going to ask the project leader, Dr. Sally Fleming, to explain all about X15. As you will understand, some information concerning X15 is sensitive and cannot be released. But following Dr. Fleming's presentation, there will be an opportunity to ask questions. Sally, over to you. SF. Thank you, Tony. Perhaps the easiest way to explain X15 is to use a concept which is already familiar. You all know that it's possible to mix metals. Bronze, for example, is made of copper and tin, and it is harder than pure copper. You also know that bronze was a vitally important material in human culture and development. Most human cultures have passed through three main ages, named after the material from which tools were generally made: a Stone Age, a Bronze Age, and an Iron Age. Now, what does all this have to do with X15? Combining metals is relatively easy. You simply melt the two metals and physically mix them. Human beings learned to do this more than 5,000 years ago. Other elements, of course, combine naturally. Hydrogen and oxygen combine to form water. But there are many substances which do not want to combine. If only we could persuade reluctant partners such as these to unite, they might produce wonderful new materials, as important to our way of life as bronze once was. Well, that's what we at New Fiber have done. By using a completely new technique for working on materials at the microscopic level, we have discovered how to combine silicon and another material whose name we cannot reveal into microscopic thread-like structures. The resulting material, called X15 for now, is both light and strong as well as extremely stable chemically. We believe that as a result of this unique combination of characteristics, X15 will have important applications in such areas as clothing and data transmission. Of course, we are still at the beginning of this exciting new field, and we still have much to learn about how to control forces and materials at the microscopic level. But I think it's important to stress that X15 is not just a chemical discovery. What we've discovered is a new technique for working on the microstructure of any material. X15 is only the first practical result of using this new technique. Part C. Tony. Thank you, Dr. Fleming. Ladies and gentlemen, I'd like to invite questions now. Could I ask you to give your name and organization before asking your question? JF. I have a question about the environment. Oh, my name is Jim Fredericks, and I'm the science correspondent for the Daily Herald. Dr. Fleming, do you foresee any environmental dangers in X15? SF. Thank you. That's an important question. X15 should pose no more of a threat to the environment than glass, which it resembles in some ways. JF. I see. Have you done actual tests to support this, or are you basing your belief just on the nature of the material? SF. Well, we wanted to make this announcement as quickly as possible, of course, but there is a program of experiments currently underway looking for unexpected effects. JF. It's possible, for example, that some other material might interact with X15 in some harmful way. SF. It's most unlikely, but that's the kind of thing we are looking for, yes. JF. Well, in that case, don't you think you should test X15 more thoroughly before releasing it into the environment? SF, I understand your concern, but I don't think we can hold back progress just because there might be some danger which we can't presently foresee. JF, or are you just trying to save money? Tony, let's move on to the next question. The person in the second, no, third row, please. LT, thank you. I'm Yoko Suzuki and I'm with K2 Television. Dr. Fleming, you mentioned clothing as a possible application for X15. Could you tell us more about that? SF, I'd be glad to. X15 has two advantages over standard artificial fibers. One is that it's stronger. The other is that it has remarkable self-healing properties. If an X15 microfiber is damaged, it can heal itself even if it comes apart completely. It can fix itself if the two halves are not too far from each other. LT. That's amazing, but as close, how flexible would it be? SF. As light and flexible as the finest silk. LT. But also long lasting? SF. Yes, indeed. A dress or suit made of X15 would last a person's lifetime. LT. That sounds like hot news for the fashion industry. SF. Maybe so, but there's a piece of good news too. X15 can be colored, of course, but its natural appearance is iridescent. It reflects light like the surface of a soup bubble or like an insect's wing. You know, bronze is a very beautiful metal. People still make ornaments from bronze. I think it's wonderful that X15 is beautiful too. Tony, ladies and gentlemen, that's all we have time for. Thank you, thank you all for coming. Please remember to pick up your information packs at reception as you leave.